All too often, there is a lack of communication between engineering disciplines working on a single project. These groups work simultaneously, sometimes without informing each other of important changes and/or issues early enough to prevent wasted time and efforts. On top of that, there could be even bigger issues occurring within project models, such as clashes between the different components that tend to get jam-packed into small areas of a plant or a building without consideration of how different loadings will affect the piping position. In this presentation, we will discuss how to merge, identify, and report interferences using Bentley's clash detection tool. Assuming that our design model starts in open plant or auto plant, we will first look at the PXF import option within AutoPIPE. We will also take a look at the mapping file components and options that go along with importing a PXF file from the plant model. Once our model is imported, our loadings are applied and our stress analysis is complete in AutoPIPE, pipe stress engineers might tend to think that their job is complete. However, we can take our model one step further by exporting a DGN model with a deflected shape in any load combination. We will look at opening this DGN model up in Bentley Navigator to run a clash detection and to detect any important clashes that may be occurring within the model. So here we will start with the AutoPIPE PXF Import. Here we will watch the initial import process of a PXF file from the design produced in open plant. The pipe stress analyst imports the PXF file that was received from open plant. He selects a code in the units as SI, and he sets up the imported piping as required, setting the specific gravity of the pipe contents, the insulation thickness and material, and the corrosion allowance. He'll transform the Z to X axis because in our AutoPIPE model, we'll work with Y as vertical, while with many CAD drafting conventions, drafters work with Z as vertical, and he sets up the operating pressure and temperature. Next, we'll see that some mapping dialog boxes pop up. The user can set the material to be used for piping, the type of supports that will be selected in AutoPIPE for a specific support name in the PXF file, and the pressure rating to be used for valves and flanges in the model. The import will be processed and the user has the opportunity to review any warning messages that AutoPIPE produces. So here we see some warnings about flange CAD lengths and a note that the operating pressure and temperature has been updated for the points in the model. We see no errors. A summary file from the import is also produced, and again, we see no errors reported here. We can view the model in AutoPIPE in solid model view, and using the review component data input grid, we see that the operating pressure and temperature information was applied to the model, along with the pipe data, including the corrosion allowance, insulation information, specific gravity, and pipe material. Also, the support types, the support friction, and support gaps were applied, and the pressure rating for the valves and the flanges has been set to 300 pounds. In watching the import process there may have seemed to be a lot of manual inputs required. A lot of these options can actually be taken care of in the mapping files that are used to create the AutoPIPE DAT model from the open plant or auto plant PXF file. The user can create user mapping files for the PXF import process. These files need to be placed in the roaming profile folder, which contains all the files that can affect an individual user's settings for the program. The program installation directory is read-only, so all the files containing settings are automatically copied from the installation directory to this user profile directory at startup. Within this directory, there are some files that are important and that could be used during the PXF import process. In this example, 3 of the user files were created by using the mapping dialog boxes that popped up during the import process. The user mapping file was created when the user selected the AutoPIPE material as A53B for the open plant material name of STL. The user class mapping file was created when the user selected the AutoPIPE support types as guide and shoe vstop for the open plant support names of @support_guide and @support, respectively. And the user rat mapping file was created when the user selected the AutoPIPE pressure rating as 300 pounds for the open plant pressure rating of CL 300. The settings that are set up in the beginning of the import process on the General Model Options dialog and the Import Open Plant Modeler Auto Plant dialog populate the cadapp.def mapping file. This file sets up the CAD files to AutoPIPE configuration. The cadapp.def file will always report units in English format. As an example, we see here that the units for the import have been set to SI, and the specific gravity of contents has been set to 1. The main PXF import mapping file is the cadapp.map file, which is a unit-independent mapping file to translate open plant and auto plant components to corresponding AutoPIPE components. It includes PXF import options, a class mapping table, a unit mapping table, a component mapping table, a support mapping table, and flange and T end connection mapping tables. The main PXF import options are highlighted here, and there's actually an AutoPIPE wiki page that explains these options in detail. So we'll open that wiki page up just to show you. So here we see a wiki page for the cadapp.map options on the PXF import process. And the question is, what options are available in the cadapp.map file while importing an auto plant or open plant PXF model into AutoPIPE? So the answer goes into the specific options that are available, and then we'll go into detail for each specific option. Most of them, if you read through, are pretty straightforward. However, if not, there is great detail of what exactly they will do during the import process to your AutoPIPE DAT model. Using the mapping tables in the cadapp.map file, many components and details of the model can be set up correctly. As an example shown here, the supports in our model can also be mapped directly in the cadapp.map file. The @support in our PXF file is mapped to a shoe here, and the @support guide in our PXF file is mapped to a guide here. If this had been set up prior to our initial PXF import, we would not have seen the mapping dialog box pop up for the support types. This support mapping callout is in the class mapping table of the cadapp.map file. From this, the support mapping table, shown in the middle, is used to assign a specific type of support. And there are also some options in the PXF import options section at the top of the cadapp.map file for importing supports. So this is, for example, where the friction value was set to 0.35 and the large upward gaps were set up in our example for our guides and our V-stops. So now that we have the mapping file set up and placed in the roaming profile folder for our example, let's run through that import process again and see how things have changed. Again, the pipe stress analyst will import the PXF file that was received from OpenPlant, and he'll select the code and the units as SI. This part is always necessary, and that's every time you start a new model in AutoPIPE. The configuration support dialog box, this is based on the catapp.def file. There's no mapping dialog boxes that pop up because these settings have been taken care of in the user mapping files. Once again, you can review the warning messages. Again, we see the same warnings, and again, we see no errors reported. And as the user reviews the review component data input grid, we see that without much manual input this time during import, the data is entered correctly for the operating case, the pipe properties, the support valve and flange data, and this is all based on the mapping files that have been set up correctly by the user. Once the PXF import is complete, the pipe stress analyst will want to apply loadings to the model. He'll want to run the analysis and then review the results. If any changes are required to satisfy code and project requirements, he would make the changes and rerun the analysis until all of the requirements are satisfied. The pipe stress and structural engineers may work together on an integrated model to include structural stiffness in the piping model and piping loads in the structural model. Once all of these steps are complete and each department believes they have a satisfactory model, the models can be exported to a DGN file to check for any clashes that may be occurring using Bentley Navigator. In our example, the user applied a user static earthquake occasional load and 2 wind occasional loads using ASCE 7-2010 to the piping model, and he'll include them in a static analysis and will review the results. Also, we assume that the pipe stress and structural teams are working together. The structural analysis is being done in STAAD Pro, so the PipeLink integration has been used to combine the piping and structural models. The piping model supports and loads were sent to STAAD. The structural engineer connected the supports to the structure from the piping, performed the combined analysis, and made any changes necessary to satisfy the structural requirements. Then he sent out the PipeLink model to be imported into AutoPIPE. The pipe stress analyst imported the PipeLink file, which contains the structural model and the support connections that the structural engineer made. And the pipe stress analyst is now ready to run the combined analysis in AutoPIPE. So now we will watch the pipe stress engineer run the combined analysis, review the results, and export the deflected shape of a critical case to a DGN model. The engineer starts by reviewing the support connections in the model. The supports are shown as connected from piping points to beam points, and he'll review the occasional loads that have been applied in the model also. So here we see the static earthquake load, and we see the wind loads. He will now set up his static analysis set, starting with a default set that includes gravity, pressure, temperature, earthquake, wind, and the support gaps and friction. His first set will assume the occasional loads are applied in the sustained case. He'll also set up a duplicate of this analysis set as a second analysis set, and this one will assume the occasional loads are applied to the piping model in the operating case after pressure and temperature have been applied. He'll run the analysis, and then he'll review the code stress results. So here we see that there's some overstressing in the sustained plus earthquake occasional case. And a lot of this, if we zoom into the area that has some overstressing, we'll see that a lot of this probably has to do with the heavy valves not really being supported enough. So the deflected shape in that sustained plus earthquake case can be reviewed, and it will give him a good idea of what supports will help. So he investigates the actual displacements at some of the points using the dialog box. It's important to remember the deflected shape is an exaggerated shape. He'll put in some supports here, 2 V-stops for the sustained case and an incline support as a guide for the earthquake case. and then he'll rerun the analysis. Once the analysis is complete, he can review the code stress results again. And what we'll see is that the same case is still producing the highest stress ratio, but it's no longer overstressed. He can use the results grid to review the displacements, and this will help determine which load combination or combinations should have the deflected shape exported to a DGN model to check for clashes. The largest movements in all of the directions here seem to be occurring in that sustained plus earthquake case. And so in our example, we will export that load combination. So here we see in the Z direction also, we have some large movements of 76 millimeters, again occurring in that earthquake case. So with this information, he will export the DGN model. He will pick the deflected shape as the GE1 shape, and he'll transform the vertical axis to Z and the X to Z to match the CAD drafting conventions in the DGN model. AutoPIPE will rerun the analysis in this coordinate system before sending out the deflected shape. And we see the export is now complete, and it can be opened in Navigator to be reviewed. Next, the engineer or the CAD designer will take that exported DGN model and will open it in Bentley Navigator to run a clash detection. Piping clashes with other pipes, structures, equipment, and or HVAC are not uncommon, and they can be very costly to redesign. In some worst-case scenarios, plants actually have to be shut down for failure investigation and repairs, so of course we'd like to avoid that at all costs. Soft and hard clashes between vessels, piping, whether it be insulated or non-insulated piping, structural, electrical, equipment, etc., they can all occur, and it's important to investigate them. Clashes are typically caused by pipes heating up and moving, but large pipe movements can also easily occur with extreme loads, such as wind loads and earthquake loads. So here we will take a look at the engineer in our example, opening the DGN model in Navigator, setting up a clash detection, and reviewing the clashes along with all of the information available in Navigator. The engineer opens the exported DGN model from AutoPIPE and starts to review the model. We can see both the original piping, structure, and supports, along with the deflected piping, structure, and supports in that sustained plus earthquake case. So here we see the original support and then the deflected support there. He will set up a new clash job, and he will add the deflected piping as set A, which will display in red, and the deflected beams as set B, which will display in blue. The information panel to the right shows the properties of the clash job. There are also options to add models, add some advanced criteria or suppression rules to any clash job. In most instances, the user would want to check more than just piping and structure, possibly including equipment, conduit, stairs, etc. So you can have rules that are set up. As an example, maybe we're interested in checking the insulation of a pipe clashing with the structure, but we consider that a soft clash instead. So continuing with this simple example, he runs the clash job, and we see 4 clashes are reported and can be reviewed. We see that all of these clashes are occurring in the same general area of the model. And if we focus in on clash 1, he can hide the background components to take a good look at which pipe is hitting which beam. Then using some tools, he can rotate and zoom into the model to take a look at the actual beam names and point names in the model. So here we can see that it is column 24 that is clashing. and it's clashing with a horizontal pipe run, which falls between point B29 at the elbow and another elbow at point B30. With this information, he can edit Clash 1 to include these details. A priority description, subject, responsible party, and status can be set up on the Details tab. He also can add an attachment, which would be a snapshot of the clash that's occurring. And we can add some comments, and in here we'll add the details about the specific column and pipe run in the comments section. Now this is just a very simple example of basically a single area of a clash that's occurring within a model, just looking at piping and structural. With the connected edition of Navigator, projects can be made connected projects, and that means that multiple users can review and update the same model. The clash list and details that were added by the user can be synced to the project so that out in the field, an engineer can use Navigator Mobile and can investigate them. If the field engineer finds some discrepancies, he could update the clash with new comments and sync it again, maybe a new attachment or picture, and sync it again for the office engineer to review. And using these tools and including as many components as are actually out in the field as possible will help all disciplines, including those out in the field, work together and avoid costly design mistakes throughout the project. I'd like to thank you for joining in on our session today about the AutoPIPE PXF Import, mapping file components, AutoPIPE DGN Export, and Navigator clash detection. And at this time, I'll hand the presentation back over to Natalie before opening the stage up to some questions and discussion.
Great. Thank you, Jessica. Before we begin the Q&A, we would like the participants to take a short poll. We would like to know, based on today's presentation, would you be interested in having someone contact you to discuss your project needs or schedule a demo? Thank you for everyone's responses. And back over to Jessica and Luke for Q&A.
Okay, the first question I received was, do I have to use an I model when exporting a DGN file from AutoPIPE for clash detection?
Okay, you don't have to use an I model. The benefit for using the extra step of actually creating an I model is to essentially create a locked file that can't be graphically updated. So like an Adobe PDF file, an I model file is locked. It can't be graphically altered, but you can add notes and measurements, and it can be verified. So this makes it a great collaboration type file format, but it's not necessary if you wish to skip this step. In our example, we actually just opened the DGN model itself within Bentley Navigator.
Great, thanks. Next question. Going through the process of exporting the PXF file from OpenPlant and then importing the PXF file into AutoPIPE, the global coordinates from AutoPIPE don't get carried over to AutoPIPE. Is there a way that AutoPIPE can read the coordinates from OpenPlant so that the two models can have the same coordinates?
Yes, in the import options, there's actually a checkbox option for that. So if I go back to there, I go back to my PXF import options. There we go. A little bit further. Okay. Up at the top, we see the append segment name to point name. That's going to change it over to our normal alphanumeric AutoPIPE coordinates, segment and point. So A1, A2, B1, B2. But if you uncheck that, then it would actually leave the OpenPlant point names to be brought in so that they would have the same names in each model.
Great. Is there, for an imported system, they've got some disconnected flanges on elbows. How do you fix this so there is no disconnect?
Okay, so again, while importing here, we have the ability to join the disconnected pipe. And you can see here in this example, we left this as unchecked. We didn't have any situations like that. Everything connected nicely. But if you go through the import process and you do find that maybe you're getting some disconnects or you're seeing some anchors randomly being placed throughout your model, that's because you have those disconnects there. So this will actually use the connectivity tolerance set over here. And within that tolerance, it will join the disconnected pipes. And you won't see those random anchors being placed throughout your model due to this option up here, which would just add anchors at any free end within your model. So using these import options will really, really be helpful in going through, looking at the wiki page and understanding what each option means.
Right, thank you. And why does AutoPIPE add anchors to points, and how do you prevent this from happening?
Okay, so that's actually similar to what we just went through. So again, AutoPIPE, if this is checked on, it will add anchors to any random free end throughout your model. And you may want that, but you may not. You may have supports towards the end and you don't want anchors. Or like I said, if it's a disconnected pipe, it's just going to add it within the model, so it kind of looks messy. So just play around with these options, whether you want the anchors. Maybe you want them at most points, but not every free end. So you just go into your model and you delete the couple of anchors that you don't want in there. After importing, you always do want to check your model thoroughly and make sure that everything looks good. So use these options to help you out. Each model would want this dialog box set up differently according to how we want that model imported.